Writing Lewis structures for covalent compounds. Writing Lewis structures is a little bit like balancing equations in that we can give you guidelines and head you in the right direction. We can tell you things that you can't do, but it's not like a stoichiometry problem where I can say, do this, do this, do this, and do that, and have it work every time. Sometimes you just kind of have to mess around with it and see what happens. And that's one of the beauty things about, that doesn't make sense. That's what I like so much about the lab we're going to do today, is you actually get models, physical models that you can mess around with your hands and manipulate them and try these different things out. And I think once you get a chance to do that, some of this Lewis structure stuff will make a little more sense. But here are the guidelines. The first thing to do is to write a correct skeletal structure for the molecule. And this is just going to show how the atoms are going to be connected. We're not going to worry about where the electrons are or anything. We'll just try to figure out how they're connected, what order they're in, kind of like a seating arrangement. Important to remember that hydrogen atoms will always be terminal. Terminal means on the end. Bless you. Hydrogen atoms have one electron. When they make one covalent bond, they then have two electrons, and that's all they're going for. That's all they can handle. A hydrogen atom can't handle an octet of electrons. It's too big. The 8 electrons is too big for the hydrogen atom. So hydrogen forms one bond. That means that hydrogen can never be between two other atoms. Okay, so it's only just one bond to something else. Another guiding idea is that many molecules tend to be symmetrical. So if you have a molecule that contains several atoms of the same type, like if you had something like carbon tetrachloride, get the right pen here, CCl4, where you've got one carbon and 4 chlorines. Symmetrical means, hey, let's try putting the carbon in the middle and put the chlorines around it. And so we might arrange it like this. And we're, instead of doing something like this and putting them all in a row. In general chemistry, we learn about inorganic chemistry, and we don't see many things that are going to form long chains of stuff. That happens in organic chemistry, which is a more advanced class, and that's not what we're studying right now. There are many exceptions. These are guidelines, and there are exceptions. The hydrogen being terminal, there's no exceptions to that one. Then you need to figure out how many electrons do you have to work with. Calculate the total number of electrons. Okay, you're going to do that by looking at each atom that's in the molecule and looking at the periodic table and finding out how many valence electrons does it have, and just add them all up. That's the number of dots that you can put in your structure. So just as a reminder, number of valence electrons for main group elements is equal to the group number. 3A, 4A, 5A, 6A, etc. If you have an ion, you need to add electrons for negative charges and subtract for positive charges. If you have an ion that has a -2 charge, how did it get a -2 charge? It's because it has 2 extra electrons, so you need to add those in. Then you put the electrons around. So you basically divide them up. You want to give as many octets as possible, just duets for hydrogen though. So a good place to start is by putting 2 electrons between each pair of atoms. If they're in a molecule, they must have at least a single bond with something else there. If there's no bond, it's not part of the molecule. So give each pair a shared bonding pair in between. And then start throwing the rest of the electrons around, trying to get 8 around everybody but hydrogen, and see what happens. Sometimes you'll run out of electrons. So when you're done distributing electrons, If any of the atoms lacks an octet, then form double or triple bonds. If there aren't enough electrons to satisfy everyone, then we need to share some more, like with the oxygen and the nitrogen molecules. Just a single bond didn't fix the situation. Oxygen needed a double bond, nitrogen needed a triple bond so that each of them could have an octet. So we take lone pairs from atoms that are on the ends and we move them into the bonding region. So let's do some examples. Write the Lewis structure for carbon monoxide. So step one is to make a skeletal structure, kind of a seating chart. And so I'm going to say, well, when there's only two atoms, it's not too hard, okay? They have to be next to each other, right? And if you put the O on the left or the C and the C on the right, that's fine. It ends up being the same. So here I've got my skeletal structure. And then I need to identify how many valence electrons. How many valence electrons does carbon have? 4. And how many does oxygen have? 6. So 4 plus 6 equals 10. I have 10 valence electrons. And now I'm going to distribute them. One way to think of this is to think of these as being children and the electrons as being cookies. And they're going to have a party. And carbon brought 4 cookies and oxygen brought 6 cookies. And you're the mom, and so you collect up all the cookies, and now we're going to share the cookies equally. The idea is to try to get everybody to have 8 cookies, but you might have to share a cookie with somebody else. So the first thing I'm going to do is I'm going to put 2 electrons between the carbon and the oxygen. There has to at least be a single bond there. So that's 2 electrons. I've got 8 more. So now I'm going to put lone pairs out here. So I did 2, that's 4, 6, 8, 10. I've run out of electrons. This is the limit of how many dots can be in your structure. This carbon has 2, 4, 6. This oxygen has 2, 4, 6. They each have 6 electrons. That's not an octet. I don't have enough electrons that I can just throw some in there. I can't just do that. Because where did those electrons come from? They can't just come out of nowhere. So what I'm going to do instead is I'm going to take a lone pair and I'm going to take this pair and I'm going to put it between so that they can share that. So I'm going to erase these guys and move them. Same number of dots. But now because this pair of electrons is shared, it gets counted by the carbon and by the oxygen. So this oxygen has 2, 4, 6, 8. Let's do the circle thing. So that oxygen has 8, and the carbon has 6. So it's better, right? It's better, but it's not good yet. Not enough electrons. What do? We share more. So there's a lone pair here, and a lone pair there, and a lone pair there. If we take this one and put it in here, that's not going to help the carbon out any, and then this oxygen's going to have too many. Let's just do that anyway. Now what do we have? That carbon still has 6. And now this oxygen has 2, 4, 6, 8, 10. More is not better. It's 8. We need 8. So how could we fix that? What if we take one of these lone pairs from the oxygen and put it on the carbon? Would that help? It would. Now how are things? That carbon, 2, 4, 6, 8. Bingo. And the oxygen? 2, 4, 6, 8. Now obviously, when carbon and oxygen bond to form carbon monoxide, they are not actually doing this with the electrons. This is a model, a way of looking at it that allows us to fairly easily come upon the right arrangement. Because there's various ways to find out what kind of a bond is between the carbon and the oxygen in carbon monoxide. And we can experimentally verify that it is a triple bond. But how would you know that just by looking at the elements on the periodic table? Well, Lewis theory is what helps us to predict that carbon monoxide has a triple bond. So if I'm going to write this in a nicer way, I might write it out like this. So each of them has 8 electrons. Remember that when you're using these lines, each of these lines is 2 electrons, because it's like you connected the dots between the 2 electrons. Each line represents 2 electrons, a bond of 2 electrons. Any questions? Yes?
So you don't have to have carbon having 4 and oxygen having 6, like starting out like we did at the beginning?
You don't. We could do it that way. Would you like to see that? Yeah, we can do that. So let's try that. So here's carbon and here's oxygen, and the carbon had 4 and the oxygen had 6. This is what we were doing for the hydrogen and bromine and nitrogen and oxygen. It didn't even occur to me that maybe we should try that here as well. Well, they're trying to share. So if we do that, now the oxygen has 7 and the carbon has 5. We're moving in the right direction. If we do this, the oxygen has 2, 4, 6, 8. But the carbon only has 2, 4, 6. So what can we do? Well, we're going to have to move some electrons. What can happen, which we don't usually talk about in this class, is that the oxygen can take this pair of electrons and share both of them. It's called a coordinate covalent bond, where both of the electrons in a shared pair come from one. It's like, oh, you poor thing, you don't have any cookies, and here I've got 4. Well, I'll share mine with you. They're sharing even though one person didn't contribute. Is it equal? No. But are people happy? Yes. And it does happen. So what's going to happen here let's see if I can do this. No? So we can just move those. Oh, done. There they are. We can just move those over. Now this becomes another bonding pair, and the carbon, these are not paired up, but that's kind of just a fluke of how we did it. But it's got 1, 2, 3, 4, 5, 6, 7, 8, and the oxygen also has 8. Is that
mastering chemistry 1?
Mastering chemistry?
Because I find that way that you just did easier to figure it out.
That's fine.
More, to be understandable.
Right.
And the other one's more like.
Well, in mastering this, what I'm doing here is I'm showing you how I'm thinking about it. It's the equivalent of showing your work. It's your scribbles as you figure out what's going on. And there are multiple approaches. This is one very valid way. And if you I actually did this for a while on the magnetic whiteboard. I had some magnet circles, and so we'd draw the element symbol, and then we'd have dots, and we'd move them around. But now I can do it on the iPad, so I don't do that anymore. But you could do that at home too, with beans or gumdrops or whatever, and say, okay, here are the electrons. Now, how can we move them around? I think one of the reasons that most books teach this other method, where you just basically pool all the electrons and then start throwing them around, it involves a lot less erasing and redrawing. But what's most important is, do you understand the process of how to get to the correct answer? So when I get this messy looking business here, then I need to redraw it neatly. And so I would have carbon and oxygen, and I've got 3 bonds, and I need to pair those up and pair those up. Now, if instead of writing that lone pair over there, you put it down here, that's absolutely fine. So where you put the lone pair, as long as it's top, bottom, left, and right, is fine. Mastering chemistry, I think it either wants you to show the dots for the bonds or the lines. I don't remember. If you read the directions carefully, it should tell you. And it is there's a little bit of a learning curve in learning how to do these on Mastering Chemistry. But once you get the hang of the little program within a program there, it's really not that bad. And you can just take your mouse and make electrons appear here or there, and then you can go and erase them and stuff. And I think it's actually easier than doing it on a piece of paper, where you have to physically erase and things get all messy and ugly. Any other questions? Let's do a couple more examples. Write the Lewis structure for H2CO. First step is to figure out how these atoms are connected. We have a couple of options here. The carbon and the oxygen are going to be connected because the hydrogens can only be connected to one thing. So we can't do something like this, where we have a hydrogen in between the carbon and oxygens, because that would mean that hydrogen would have to form 2 bonds, and it can't do that. It can only form 1 bond, so that's not going to work. Oops. So the carbon and the oxygen must go together, and then the question is what to do with the hydrogens. Well, I could put 1 on each side, because she said they were supposed to be symmetrical. Or we could put both of the hydrogens on the carbon, or we could put both of the hydrogens on the oxygen. Those are the 3 possibilities. Now, there are some guidelines that we haven't talked about yet. And I didn't tell the morning class this, but I'm going to tell you guys. Let's look at the Lewis structures for these individual atoms. Carbon has 4 valence electrons. So when we look at its Lewis structure, we see that it has 4 unpaired electrons. Carbon is going to tend to form 4 bonds. And looking at this, here the carbon looks like it's probably going to end up with 2 bonds. This one, it's going to have a minimum of 3 bonds. And this one, it looks like it's only going to have 1 bond. If we suspect that carbon wants 4 bonds, which one of these possibilities is probably better? This one, right? We're going to have a minimum of 3 bonds. There has to be a bond there, and a bond here, and a bond there. So that's closer to 4. Oxygen. Oxygen has 2 unpaired electrons. Oxygen tends to form 2 bonds. And when we look at it paired up like this, that makes sense because this electron is alone, just kind of waiting to be shared. And this one's alone, just kind of waiting to be shared, just like these guys. Hydrogen forms 1 bond, it has 1 unpaired electron. So that can give you a clue. Look at the Lewis structure for the element by itself, just a single atom, and look how many lone unpaired electrons are there. That's the number of bonds. Nitrogen has 5 valence electrons. How many unpaired electrons? 3, right? This one, and this one. When we did nitrogen, the molecule, it formed a triple bond. That's 3 bonds. Nitrogen tends to form 3 bonds. So based on that, I'm going to select this one as the most likely probability. Now the next step is identifying how many valence electrons do we have. We have 2 hydrogens. Each hydrogen has how many valence electrons? 1. And how many does a carbon atom have? You guys need to wake up. 4, thank you. And oxygen? 6. There are 2 hydrogen atoms in the formula. So each of them brings 1 electron. 2 of them together will bring 2 electrons. So if you have more than 1 atom of a given element, you need to multiply. Just like when we did molar masses. So we've got 2 plus 4 plus 6. Pretty sure that's 12. We have 12 dots to mess around with. So I am first going to put dots between each pair of atoms so that there's a bond. That used up 6 of my electrons. And now I'm going to try to give octets to carbon and oxygen. The hydrogens are already happy. So I've got 2, 4, 6, 8, 10, 12 out of dots. Is everybody happy? No. Who's not happy? The oxygen. Oxygen is not a happy camper. It's only got 6 electrons. It's like, I came in with 6 electrons and I'm sharing with you and I still only have 6 electrons. This is not right. So what we need to do is we need to move a lone pair. There's a lone pair here and there's a lone pair over here. Now, if we move the lone pair from the atom that already is missing some electrons, that's not going to help. You want to take the electrons from the one that has more. So I'm going to take these 2 electrons and move them over there. Because in that way, the carbon still has 8. 2, 4, 6, 8. Now this oxygen also has 8. 2, 4, 6, 8. So there's a good Lewis structure. Let's look at doing it the other way. We got hydrogen and carbon and oxygen. And these each had 1, and this one had 4, and this one had 6. So this is looking at the individual atoms with their valence electrons and then seeing how can I put them together, how can I have them share. Well, you could have both of these hydrogens share with the oxygen and they'd all be happy, but that would leave carbon out and you'd end up with water, and carbon has to be included in here somewhere. The hydrogens are going to attach either to the carbon or to the oxygen, and so let's leave those out for now. Let's have there be a connection here with the carbon and the oxygen. So oxygen's getting closer. It's got 2, 4, 6, 7. Carbon's got 2, 3, 4, 5. So what would happen if we took the hydrogen and moved it over here and had it share with the oxygen? Now the oxygen is happy, right? Oxygen's happy. And then we could take this guy, oops, that's not what I wanted to do. We can take this, that's not what I wanted to do either. Take this guy and move him over here and say, let's make a bond there. Like, oh, well, that's good. It's better. So we got 2 hydrogens are happy and the oxygen's happy. Is the carbon happy? No. So we need to do some more sharing. Carbon doesn't have any buddy it can really share with because oxygen's already happy. So what we would need to do is we would need to take electrons from here and put them over there and then pair these guys up. So there's a bond and these guys should be paired up, so I'm going to have to erase that one and move it over there. Now that's not the same as the first one I drew, is it? The first one had 2 hydrogens attached to the carbon and a double bond between the carbon and the oxygen. And this one has hydrogen to carbon, double bond to oxygen, and then to hydrogen. At this point in your chemistry career, if you drew this, I would say, that's good enough. That's okay. It follows the rules. The hydrogens have duets. Each of these carbon and oxygen atoms have octets, and that's what we were going for. But it doesn't work so well with this little extra that I told you up here, because carbon likes to have 4 bonds, and down here, carbon has 3 bonds. 1, 2, 3, and a lone pair. Carbon doesn't like to have lone pairs. And over here, oxygen has 2 bonds, plus this one is 3, and oxygen doesn't like to do that. So this is not a great Lewis structure. So let's back up to that point. So let's back up farther, just because we can. Back to where we were deciding where to put the hydrogens.
Couldn't you just connect both hydrogens
To the carbon?
carbon?
Yes, I could.
Carbons to the oxygen?
So I could do that, and then I could do this. It's like, well, why did you do the other one? Well, because I knew that some people would try to do that, and it's not all bad. It's just not ideal. But I think with this slightly more complicated molecule, you see that drawing the individual atoms and then trying to rearrange them in some ways is a little more complicated. It involves more scratching and erasing and moving around. But if it makes more sense to you, go right ahead and do it. So what about when we have polyatomic ions? We're going to follow the same procedure. We just have to be concerned about the charges. So if there's a -1 charge, you add 1 electron. -2 charge, you would add 2 electrons. If it's a positive charge, you have to subtract electrons. And then just like we did with the monatomic ions, we're going to put brackets and write the charge on the outside, except in mastering chemistry. So let's do the cyanide ion. So here's carbon and nitrogen. And carbon has how many valence electrons? 4. And nitrogen has 5. And the charge on this is -1. Does that mean we have an extra electron or we're short one? Extra, because electrons have negative charges. If the ion has a negative charge, that means there's extra electrons. So I need to add 1 for the negative charge. So 4 plus 5 plus 1, I learned this morning, is 10, not 8. Yeah, you learn something new every day. So we need to put a pair of electrons between the carbon and the nitrogen to make a bond. So that's 2 electrons, 4, 6, 8, 10 out of electrons. So then I'm going to take these electrons and move them and that's better. Here, I'll draw a line here so we can see more clearly. That's a bond. We're better, but the carbon's still not happy. So I'm going to take these electrons and move those and make those a bond between. And now we're happy. Then we have to put brackets and the charge on the outside. And you might want to redraw that so it looks a little prettier. And that's the Lewis structure for the cyanide ion. So things like nitrate ion, ammonium ion, we can draw Lewis structures for those as well. So what we're going to do now is I'm going to stop this recording before I go on.